Okay, so let's start. So we'll see some more facts over the Smith chart, and then we'll go to some problems that how we can solve by using the Smith chart. So before that, some of the things I would like to clear, and one of the very important point, because you will see also these things, that how we can relate actually that gamma in and gamma L. Okay, reflection input reflection coefficient and the load reflection coefficient if the transmission line is lossy. Correct. So if the transmission line is lossy, okay, then what will be the relation between gamma in and gamma L? Correct. We'll try to see these things today. It's very important, and one of the Smith chart problem actually based on these things. So it is somewhat it's necessary to learn here. So we know that gamma L is equal ZL minus Z naught over ZL plus Z naught. Correct. And gamma in input reflection coefficient is Zin over Z naught Zin plus Z naught. Fine. So what is the difference? The difference is actually here we have ZL, here we have Zn. Correct. So this is actually the reflection coefficient at particular load location, and this is the reflection coefficient, okay, at the input side where we are going to feed the system. Fine. Now another definition we have, if the transmission line is lossy actually, so what we can write Z in. Z in is actually Z naught 1 plus gamma L e to the power minus 2 gamma Z dash. Instead of writing beta here, now we have to replace with gamma. Gamma is alpha plus j beta. So alpha will be in a picture, and that will be the part means will show the things related to the attenuation. Correct. Gamma L e to the power minus 2 gamma Z dash. Fine. Okay. So now if we have Z in, definitely one can find it out the gamma in. How we can find it out the gamma in? Gamma in we can write like this: Z in over Z naught minus 1 upon Z in plus Z in by Z naught plus 1. Normalized way. I'm writing here. So we are recalling this term here, correct? So this will be 1 plus gamma L e to the power minus 2 gamma Z dash over 1 minus gamma L e to the power minus 2 gamma Z dash minus 1, and the same thing will be in the denominator, 1 plus gamma L e to the power minus 2 gamma Z dash over 1 minus gamma L e to the power minus 2 gamma Z dash. Fine. And this is plus 1. Now we have to solve this. Correct. We have to solve this. So if you are solving this, so the gamma in will be gamma e to the power minus 2 gamma Z dash. Fine. So this is one thing we got. Now we can relate actually this way. This is gamma L. Sorry. This is gamma L. Okay. So now we have our relation. You can see here. Correct. Now let us try to analyze these things. Okay. So what we can do actually, this we can explain like this: mod of gamma L. Okay. E to the power j theta gamma. Okay. So the thing is, magnitude and the phase we written separately, and we can open it these things to alpha plus j beta Z dash. Correct. What is the benefit actually? The benefit is that now we can write the right hand side as well in a magnitude and the phase form is like that. right? Now we need to compare actually the real and imaginary parts here. So if you compare these things, so you will be having, if you are comparing the real part, so real part will be mod of gamma in is equal to gamma L e to the power minus 2 alpha z dash. Fine. So what we can write actually, that the ratio of mod of gamma in and gamma L is equal to e to the power minus 2 alpha z dash. Now this quantity is known to us, z dash is also known to us, so we can relate actually that how much decay, okay, or how much uh, uh, decrease in amplitude of gamma L and gamma L, we can relate it, okay. And if we compare the imaginary part, so what we can write, gamma theta gamma in is equal to theta gamma minus 2 beta z dash. Okay, so now we can relate the phase and as well as the magnitude. Correct. Now, if you take on a special case, correct. If you take in a special case where let's say alpha is equal 0, so the same situation we analyze many times. So in that case, what we can say that gamma in mod of gamma in is equal to gamma L. Fine. So now the thing is, if it is in a problem that gamma L is given to you, okay, so you can find it out gamma in just dividing e to the power 2 alpha L or z dash, whatever the distance. Okay? So this is one of very important relation. You please note it down. Now we'll study actually the matching of arbitrary load line. Fine. So we'll see one problem actually in, after all on this concept, correct. But before that, there's a one more thing I would like to discuss with you. It's very important to solve the problem with the Smith chart. So matching an arbitrary load to line. Fine. So how we can do actually this thing? So using the single open or short-ended uh, lines, means transmission line sections. Okay, as a single step, like we can connect with a parallel or a series, and this could be managed actually with this, and we can have a match system, because ultimately when we are talking about the matching, it means that we need to balance the capacitance and inductance. So we already have the idea that the segment of the transmission line depends on the electrical line. It behaves like a capacitor or inductor. So that property could be utilized. Now based on the requirement, you can connect with these things in a series or in a parallel. Correct. So basically, in a coming classes, we'll see the impedance matching by using the single step and the double step, and these are in mainly in a parallel actually. Correct. So the thing is, why we are doing this thing, because the calculation is somewhat is easy actually. So the thing is, when we are doing this kind of thing, so we need to make the calculation in terms of admittance instead of impedance. Okay, so because the connections would be parallel actually. The connection would be parallel. In series, it is somewhat quite challenging actually. So parallel, we can manage these steps and all. So we have to learn that how we can use the Smith chart, the same Smith chart for the admittance case. Okay, so let us discuss some of the points actually. So first, we examine how the Smith chart can be used to make admittance calculation. Correct. So here, let YL is the load admittance is actually equal to 1 upon ZL. Fine. This denotes what? The load admittance. Fine. Now we know already these things that ZL bar, which is a normalized one, is ZL by R naught. Okay, these things we know. We can also write down these things 1 upon R naught YL, or finally we can do like this YL bar. This is one equation. Or we can also write these things YL, okay, YL bar. This is what? Normalized load admittance. This is what? Normalized load admittance. Fine. We can also write this YL over Y naught. This is also true. Okay. Or YL over G naught is equal to R naught YL, the same thing you can see here. And finally we can express as G plus JB, like we represent earlier R plus JX. In a similar way here we can do G plus JB, where G is actually normalized conductance, whereas B is normalized susceptance. Okay. Now, if you carefully see this equation number 1, so this suggests actually a quarter wave line. Okay. What it suggests? This is a quarter wave line. We can prove actually, because we already have the idea about the quarter wave transmission line. We have seen that how we can convert or we can transform the impedance. Correct. So let us do one more time actually, and we'll try to show that this particular equation number 1 is actually the suggest actually the quarter wave transmission line concept. Okay, how we can do these things. So for L is equal lambda by 4 line, I'm talking about L is equal to lambda by 4 line. So for this we already have Z in is equal Z naught square over ZL. Remember these things? Okay, or we can also write Z in over Z naught is equal Z naught over ZL. Fine. Now, if you see this term, this is actually, we can write the normalized one as well. Means Z in bar. We can write as Z in bar. Fine. And the right hand side term, we can write as 1 upon ZL over Z naught. Can we write down? Yes. It's not a big deal. Correct. Writing all the things in a denominator. Now, finally, we can do 1 upon ZL bar. Correct. Now, what you can see here, that Zin is equal 1 upon ZL bar. Or we can also say the YL bar. This is the same thing actually. Correct. You can see here. Okay. Now the thing is, theoretically we can do like this. There is no problem with this. But the thing is, on the Smith chart, how we can do? We need to do over the Smith chart, because these all of the things. And I told you in the last class, this whole Smith chart is lambda by 2. The elliptical length, if you see, this is lambda by 2. Correct? Okay. So it means if we see the lambda by 4, so we can see that half of the circle we have to travel it. Okay, to do these things. Fine. Okay. Now, just a minute. Okay. So another thing we have seen that phi is equal theta gamma. Remember these things, 2 beta z dash. Correct? So what is that actually? This is a transmission line, let's say, of length d. Fine. This is a generator and this is a load here. This is a transmission line of some impedance, characteristic impedance Z0. Fine. This is we know already. Correct. We will not talk about more on these things because we have the proper background of the transmission line. So let's say if at z dash is equal 0 means at load side. We are at load side. Fine. When I say z dash is equal to 0, it means I'm here at the load side. Okay. So in that case, phi will be theta gamma. Remember these things we already used. Okay. This equation. Okay. Now, what we can do actually, the reflection coefficient. Okay. Gamma d. Okay. The gamma d we can write at the generated side like mod of gamma e to the power j theta gamma. Fine. Now another relation we have these things in terms for Zin. So Zin at d, correct? We have seen Zin as a function of z dash. Remember this thing? So I'm talking about particularly at d, correct? So what we can write actually these things 1 plus gamma is a function of d e to the power minus 2j beta z dash. We are taking here the lossless case. Fine. Now, if I say, let's say if I say z dash is equal 0, correct? It means I'm at the load side. Okay. Now, in that case, that Zin, this will be 0, is equal to what? This will be 1 plus gamma d, 1 minus gamma d. Or in a phase and magnitude form, we can write 1 plus mod of gamma e to the power j theta, this things, theta gamma, 1 minus, just a minute, 1 minus mod of gamma e to the power j theta gamma. Fine. So this is what? This is Zin actually. Correct? This is Zin. Now, can we find it out y in? Of course, y in, we can find it out. These all are the normalized value. Please take care. These all are normalized value. I forgot to put the bar. These are all normalized values. Okay, we can do like this. And this would be 1 minus mod of gamma e to the power j theta gamma divided by 1 plus mod of gamma e to the power j theta gamma. Fine. So the thing is, finally we have the y in, okay, in terms of the reflection coefficient. Now, let's say if I'm saying that gamma is a function of d and I'm adding an extra length of lambda by 4, then can we calculate? Yes. So this will be mod of gamma e to the power j, and what we need to do, theta gamma minus 2 beta lambda by 4. Correct? Can we do? Yes, definitely. Because if you remember, what was the phi? The phi was actually theta gamma minus 2 beta z dash. And what is z dash? Z dash was the extra length. And here, this extra length is lambda by 4. Correct? So particularly at lambda by 4, we want to observe the things. Correct? Now, if you solve these things, how you solve? Mod of gamma e to the power j theta gamma into e to the power minus j, this is pi by 2. Fine. And simply you can write minus gamma d. Correct? Fine. Okay. So it means that you have to do these things. Okay. So now the thing is, if you find it out z in d plus, let's say lambda by 4. So what will be the formula? 1 plus reflection coefficient is a function of d plus lambda by 4 divided by 1 minus reflection coefficient d plus lambda by 4 at this distance. Now can we solve? Yes, we already have the solution for this here. You please check. So what we can write, this is 1 minus gamma d and 1 plus gamma d. Now what is this actually? We already have this thing. This is actually what? This is the normalized input admittance, correct? So we can finally write y in the function of d, normalized one. It means what? If we do, or if we walk over the lambda by 4 over the Smith chart, so that point where we will reach will call as a y in, okay, admittance. So it is so simple now. If you have a point over the Smith chart, and that point will be telling you the normalized impedance. Opposite of that point will provide you the admittance. That's all. Correct. Or otherwise you can just walk over the Smith chart of the lambda by 4, and that would be the point of y in. Correct. So this is so simple actually. Huh. So in this way, the things could be utilized on the same Smith chart. Otherwise, you have to manage a admittance chart where you can do all this kind of calculations. Fine. So now here, I'll show you this thing. These are two Smith chart. Correct. So here, this one is what we studied actually so far, and this is actually, this one is the impedance Smith chart, and this is admittance. Okay, it means this is z is equal r plus jx, whereas this is y is equal g plus jb. Okay, here it means z is a function of d. We can write 1 plus gamma, 1 minus gamma is a function of d. Here y bar d is equal 1 minus gamma d, 1 plus gamma d. Just what we solved actually. Correct. So now we have two Smith charts. You can do this. You will be getting the separate Smith chart for in terms of the these things, admittance and impedance. I already told you that how you will manage these things. Now here the things are this little bit opposite actually. Like here we have a this thing open circuit, then we have a short circuit. Sorry. This is actually the open circuit and this is the short circuit. And in that case, okay, here this point is a short circuit and this is again an open circuit. Fine. So you can say this is a dual of this thing. So either you can go with the impedance chart or admittance chart, both will work. But normally what we will do, that we are converting, let's say if the ZL is given or Z points are given, so we are moving just lambda by 4 over the Smith chart and we are getting y. Okay, this is the admittance. Correct. So let us solve one problem actually and we'll see that how we can manage these things. Okay, so let's say we have a Smith chart here, and this is an example actually of the book. So it is given here that ZL is equal, this is 25, sorry, this is 25 plus J 100. Okay, what is it? This is a load impedance, it is given, and the characteristic impedance is given as R0 is equal 51. You need to find it out YL. Can we find it out YL? Yes, definitely. So what we need to do? Please check all the steps here. So first we need to normalize it. Okay. First we need to normalize. How we normalize? You just divide with ZL over R0. So this will be ZL bar. And this will be 0.5 plus 2J. Correct? It means R plus JX. Now what you need to do? You need to find the R circle of 0.5 and X circle of 2. correct? So if you see the Smith chart, if you see the Smith chart, so the 0.5, okay, where you're getting the 0.5, this circle, this, if you see here, correct, 0.5, okay, this is the circle. If you're tracing, this is like that, correct? Whereas the 2, which is x value, so x value you can find it out that somewhere here, okay. It means that this circle of x and 0.5, which is the R circle, this circle. So this is intersecting this thing, intersect at the point of this point, okay. So this point is actually what? This is 0.5 plus 2j, okay, over the Smith chart, correct? Over the Smith chart, you have this point. I hope this is clear to you. You can also find over the Smith chart and you can point it. Fine. Now what we need to do here, we need to find it out the y bar actually, correct? Y bar, YL bar, okay, or YL. So as I told you that we need to move lambda by 4. Okay, we need to move lambda by where? Towards the generator, because we are at the load, correct? Now you have to read the scale actually. So the outer scale, if you see, this is wavelength towards the generator, whereas the second scale, if you see, this is wavelength towards the load. It means that this scale we have to read, correct? Now we are at this point, correct? We are at this point, fine. So we have to move lambda by 4. So what you need to do, okay, you have to mark it a point here over the outer scale, and you need to add 0.25 on this. So what you will see actually, if you add 0.25, so you will be exactly going opposite of this point. Okay, means if you take a scale, correct? If you take a scale and just match these two lines, correct? Okay, and at the same length you extend somewhat here, correct? So you will be getting a point which is actually y l bar, and if you read this point, correct, this is yl bar is equal 0.12 minus 0.47j. And what we need to do, we need to again these things divide, correct? So yl will be 0.002 minus j 009. Fine. So in this way you can find it out your yl. So this is not a big task actually. So but you require exact points over the Smith chart. You need to find it out, correct? You need to find it out, then only you can do all kind of things. Otherwise, if any small mistake will lead you, the whole problem is going in a wrong direction, correct? So you need to be very careful pointing over the Smith chart, correct? So in this way we can find it out the admittance over the Smith chart. Fine. Now one more problem we can do actually. Okay, so this is again an example actually. So here the problem statement is find the input admittance of an open circuited line of characteristic impedance of 300 ohm and length 0.04 lambda. Okay, so the problem is very clear actually. The transmission line length is given to you, which is 0.04 lambda. Okay, and characteristic impedance is given as 300 ohm. Fine, and this is open circuit. At this point, this is open circuit. So what you need to find? You need to find the Y in. How you will find it out? Correct? How you will find it out? So what you need to do first, you need to find a point of open circuit. Correct? You have to find the point of the open circuit over the Smith chart. Okay, so let's mark over here. This is O, a center, and this point, this particular point is a P open circuit. Okay, and if you read carefully the scale, this is 0.25. Fine. So right now, okay, on the and please mention this. Please take care this thing that we are reading the scale of wavelength towards the generator. Correct? Because right now I'm talking about at the load side. Correct? Which is the open circuit. Fine. So this is 0.25. Okay. Now this is the point where the load is sitting. Means this is the open circuit. Now what we need to do, if we move on the Smith chart, okay, 0.04 lambda towards the generator, okay, so we can reach at the input side. It's clear to you? It's clear to you? I hope so. So what we need to do, we need to add actually 0.25 plus 0.004 lambda, and the outcome is 0.29. It means that we need to find 0.29. So if you check this on the Smith chart, so this is the point over the wavelength towards the center. This is 0.29 lambda. Correct? Now what you need to do, you just match it. Fine? Just match these 2 points. It means what? This is what? This is actually Z in bar. What is this? This is Z in bar because from open circuit you traveled 0.04. Okay, from open circuit you traveled 0.04 and you reach at the scale 0.29 lambda, which is nothing but at the location of the generator side. Okay, so now what you need to find it out, you have to find it out the input admittance. Now the things are very easy. Again, you need to add 0.25 lambda here. So this is, if you add these things, these two numbers, 4, 5. So you need to find 0.54 lambda. Now on the wavelength towards the generator, if you try to find it out, these things 0.54. Okay, so where you are getting these things? Can you see these things? Or you can go opposite of these things also. Fine, because when you travel these things, so you need to separate it out like 0.5 plus 0.04. So 0.04, if you see here, so somewhere here actually. Okay, so you just match these things like this. Okay, you have to match this thing. So this is the point actually. This is the point. Fine. So now you can read the scale actually, and you can get the idea here that yi is equal to 0 plus j. Okay, there will be only x here 0.26. Okay. Now what we will do, 1 upon 300 into this term j 0.26, and the answer will be j 0.87 millisiemens. Okay, so this is your input admittance. Fine. I hope this is clear to you, and it requires a practice over the Smith chart. Correct. I cannot draw the very precisely. It requires a geometry box and all the things. But the roughly I mark the point. I match the lines. Correct. But you need to do precisely. Correct. You need to do precisely over the Smith chart. Otherwise, okay, the things will not be very much clear. Okay. So you can read all the scale. Okay. So you have to like how I read 0.26. Like here, if you see, these are the things actually. Okay, these are the X scale. If you see, so this is somewhat here actually. If you see this scale, so this is somewhat at this point. So this is 0.626. So in this way, I read the scale and yeah, I manage like this. Correct. So in this way, like over the Smith chart, you can do uh, these things to find it out the admittance. Correct. Precisely. Correct. So this is all about. And there is one problem actually I want to discuss, but it requires a time. So what you can do, you can find in a book. You can find in a book there's a one problem based on the relation of gamma in and gamma L. Correct. So otherwise, you can see these things, some other examples as well related to the matching and these things initial level. Correct. And we will discuss in the next class. So this meeting is going to be end within a minute. Correct. So you can rejoin, and if you have any questions, you can discuss with me. If you have any doubt of marking over the Smith chart, you can discuss with me. We have still 5 to 10 minutes in a class. Okay, so please rejoin after this thing and we can discuss.